Using AI for ecological risk mapping. Key concepts and frameworks. EPD-Net, filling the gap. Development of ecological planning and design learning network and an adaptive smart training module for disaster resilient and sustainable cities. Content of the presentation. Learning objectives. AI fundamentals in ecological risk mapping. Defining artificial intelligence, AI. The need for AI in ecological risk mapping, core AI paradigms for environmental applications. AI for core contributions. Core AI technologies, machine learning, ML, in deep learning, DL, powering complex analysis. Explainable AI, XAI, the imperative of trust. Key requirements for responsible AI, the 7 pillars, integration frameworks. The AI application workflow in ECO-DRR. Data preparation. Risk elements and sources. Integrating ecosystems with DRR via AI. AI application scenarios by ECO-DRR procedure. Best cases and summary. Best cases. AI in ecological risk reduction. Summary. Using AI for ecological risk mapping. References. Understand core AI concepts in the context of ecological risk mapping. Explore machine learning, deep learning, and explainable AI, XAI, review frameworks for integrating AI into ecological data workflows. What exactly is artificial intelligence in this context? We define AI as a system's ability to interpret external data correctly, to learn from such data, and crucially, to use those learnings to achieve specific goals and tasks through flexible adaptations. This capability is what makes AI so disruptive. In terms of urban data, AI allows for the fast and accurate analysis of large data volumes. When we look at the application in the broader urban environment, in smart cities, AI is primarily used to innovate and improve the delivery of public services. It drives efficiency and enables systems to operate at scale. But why is AI essential for our topic, ecological risk reduction? The challenge in ecosystem-based disaster risk reduction, or ECO-DRR, is its inherent complexity and uncertainty. Traditional engineering measures often fall short. AI, when applied reasonably, effectively addresses the uncertainty and complexity problems faced in urban ecosystems and natural hazard impacts. It moves us beyond simple data collection to actually automating problem-solving and decision-making processes, ultimately helping us build smarter, more resilient cities. On this slide, we address the critical why behind integrating AI into environmental management. Firstly, the global context is dominated by rapid urbanization. With the proportion of people living in urban areas projected to grow to 68% by 2050, urban spatial elements and population density continue to increase. This highly urbanized population faces increased risks. Climate change and the mismanagement of land and resources are triggering and intensifying natural disasters. The leading international approach for addressing this is ecosystem-based disaster risk reduction, or ECO-DRR. While valuable, ECO-DRR presents unique challenges compared to traditional, engineering-based DRR. Specifically, the complexity of ECO-DRR is high. The aims are often broader and vaguer, and evaluating ecosystem performance is challenging. For instance, measuring complex parameters like ecosystem service provision, biodiversity, and environmental health is inherently difficult to monitor. This results in labor-intensive and computationally heavy work. This is precisely where AI steps in as a solution. AI technologies can effectively address the uncertainty and complexity problems inherent in urban ECO-DRR. By automating complex computations and enabling better adaptation, AI helps save significant computing and labor costs, transforming ECO-DRR from a complex, passive approach to a proactive, sustainable strategy. To understand how AI functions in ecological applications, we need to look at the 3 core paradigms, or fundamental types, of AI algorithms. These categories are defined based on the objective the AI system seeks to achieve. The first paradigm is learning. This category is crucial because it moves computers beyond simple data filtering to sophisticated deep learning. Learning algorithms, such as neural networks, are essential for identifying complex relationships and predicting outcomes based on patterns in massive datasets. Next, we have discovering. The objective here is to classify and cluster the data displayed in complex scenes. Discovery algorithms, like k-means or k-nearest neighbor clustering, are highly effective in environmental applications for tasks such as spatial partitioning, spatial characteristics extraction, and classifying urban trees or green spaces based on functional indicators. Finally, the third paradigm is reasoning. Reasoning stems from induction and deduction to generate heuristics and mimic human perception and decision. Technologies like expert systems and fuzzy logic fall into this category. Reasoning algorithms allow us to perform complex evaluations, such as assessing the co-benefits of eco-DRR with fuzzy logic or performing real-time control of green infrastructure facilities. These three paradigms form the foundation for selecting the right AI tool to match the specific aim of an ecological risk reduction project. Now that we have established the need for AI and understood its core paradigms, let's focus on the direct contributions of AI to ecological risk mapping. One of AI's most powerful contributions is automated analysis. AI has the potential to accelerate the decision-making process by automating complex statistical analyses. This capability is particularly relevant when dealing with vast amounts of environmental data, helping to reduce economic uncertainty and assist in critical decisions. Secondly, AI excels at pattern recognition. Deep learning, in particular, has had success recognizing patterns from a wide range of data sources, including images, audio, video, and other sensors. This allows us to optimize data management processes and identify everything from coding errors to potential cyber attacks. Thirdly, AI is a game changer for environmental monitoring. AI systems can monitor changes in the environment, including noise, temperature, humidity, emissions, and water pollutants. More importantly, AI systems can respond to these changes and quickly implement solutions for dealing with any emerging issues. Finally, AI leads to enhanced modeling. The improved data quality resulting from AI analysis contributes to developing more robust and accurate environmental modeling systems. This foundational work is vital for forecasting future risk development and enabling dynamic planning, which we will explore further in the next sections. Moving into the specifics of AI technologies, we focus on machine learning, or ML. ML is arguably the most commonly used AI paradigm in eco-DRR applications today. The core objective of ML in this field is multifaceted. It is used to make spatial partitioning, identify key indicators, and significantly improve model prediction performance. These capabilities translate into vital key applications for ecological risk mapping. ML algorithms are utilized for comprehensive tasks like risk grading zoning, promoting desirable environmental patterns, and conducting crucial multi-objective trade-offs. For instance, optimizing cost-effective green infrastructure solutions often relies heavily on ML. At its heart, ML is powerful because it enables systems to identify patterns from vast and diverse datasets. This includes everything from remote sensing images to audio and sensor data collected across the urban ecosystem. We see this realized through various ML technologies. Prominent examples include neural networks, which can identify various feature values of disaster risk with low error, the random forest algorithm, essential for evaluating the relative importance of indicators, and various regression algorithms used to assess variable correlations. Next, we delve into deep learning, or DL, a highly sophisticated subset of machine learning. DL's core function in ecological and urban applications is automating complex data fusion processes. Data fusion itself is the critical process of taking data from a variety of sources, combining it, and improving its overall quality and usefulness. Given the complexity of urban ecosystems, where data comes from sensors, satellite imagery, traffic systems, and more, this ability is indispensable. The computational power of DL is transformative. DL can conduct statistical analyses that are much larger and more complex than could ever be completed with human intervention. This capability significantly accelerates the decision-making process. We see practical applications in across various domains. For instance, DL is highly effective for accurate land cover classification from remote sensing imagery. This is vital for understanding vulnerability factors. Furthermore, DL models are used for monitoring complex data, such as real-time traffic flow, which contributes to transport optimization and reducing emissions, linking environment and infrastructure. A powerful example is the use of deep convolutional neural networks, or CNNs, for urban scene analysis. CNNs can automatically process visual data, like aerial images, to differentiate spatial structures, which is critical for mapping and planning. As AI systems become more powerful and complex, particularly deep learning models, we face a critical challenge: the imperative of trust. We must acknowledge that ML systems can often be perceived as black box models, making their outcomes and decisions hard to verify. This challenge is encapsulated in the inherent AI risks, often termed the black box effect. These risks include opacity, complexity, unpredictability, and partially autonomous behavior. If we cannot explain why an AI system recommended a specific ecological intervention or predicted a certain flood risk, its utility and public acceptance diminish. This is why explainable AI, or XAI, is so crucial. The XAI solution ensures transparency, adaptability to varying environmental conditions, and accountability for performance. These characteristics help systems maintain compliance with existing laws meant to protect fundamental rights. Ultimately, trust is paramount. The success of AI deployment in making our cities smarter will depend on the knowledge and care with which these technologies are deployed responsibly. Planners and public managers must consider how social license impacts their ability to deploy emerging technologies. This leads us to the concept of responsible innovation. AI systems must be designed using a value-sensitive design approach and need to account for the multiple aspects of diversity that are omnipresent in our cities. Building on the need for explainable AI, we must establish clear requirements for its deployment. Responsible AI application in cities is vital to protect fundamental rights. If we fail to do this, the risks of advanced AI could severely undermine public trust and welfare. Fortunately, we have frameworks to guide this. The European Union, for example, has established 7 key requirements for a successful AI utilization. These are often referred to as the 7 pillars of trust and safety. First, human agency and oversight. AI must enhance, not replace, human control and decision-making. Second, technical robustness and safety. This addresses traditional security, ensuring technologies are protected against hacks and vulnerabilities. Third, privacy and data governance. A focus on privacy by design is needed to enforce a citizen-centric approach to data collection. Fourth, transparency. Users must understand how AI systems reach their decisions. Fifth, diversity, non-discrimination, and fairness. AI systems must account for the multiple aspects of diversity in our cities to prevent biases, such as those seen in certain facial recognition software. Sixth, societal and environmental well-being. This aligns directly with our work, ensuring AI contributes positively to sustainable development and environmental outcomes. And finally, accountability. There must be clear mechanisms for reporting, auditing, and providing feedback on the performance of these systems. By adhering to these requirements, we can ensure AI is used responsibly to tackle our most complex urban challenges. To successfully integrate AI into ECO-DRR practice, we must follow a clear, structured workflow. This process ensures the AI application is aligned with our ultimate goals. The workflow starts with data preparation. AI relies on data and information to learn, discover, and reason. Therefore, this stage involves sourcing, cleaning, structuring, and sometimes labeling raw data to make it usable for the models. Next comes algorithm selection. This crucial choice must align with the objectives the AI seeks to achieve, which themselves must connect to the aims of ECO-DRR. For example, a learning algorithm might be selected for risk profiling, while a search and optimization algorithm might be chosen for decision-making. Finally, we reach model application. This is the deployment phase, where the selected algorithm is used to achieve specific tasks, such as multi-objective trade-offs or real-time control. However, the foundation of this entire workflow is a clear prerequisite: defining the ECO-DRR aims. The scale and type of the natural disaster risk, whether it is a site-level flood or a regional heatwave, is what dictates and guides the aims of the ECO-DRR project. Data foundation is essential for the implementation of AI applications. This slide outlines how we prepare the necessary data, which must effectively support AI applications. The data is categorized based on the 3 classical elements of disaster risk: hazard, vulnerability, and exposure. Hazard data selection is closely related to the type of disaster. For climate-related disasters, like floods and heat, meteorological data is the primary data source. Conversely, non-climatic disasters such as earthquakes necessitate the use of geological data. Vulnerability data is the most frequently used category in ECO-DRR studies. Indicators often include digital elevation models, DEM, land cover, and land use. For stormwater management cases, hydrology and urban drainage facilities data are highly frequent. For exposure data, we focus on population and economic figures, which are already extensively used. However, data on people's awareness of risks, collected via questionnaires and public participation, is also important. Finally, we face a crucial data challenge. Raw data, such as that derived from remote sensing or historical disaster records, must undergo processing like classification and structuring to ensure AI readiness. This preparation stage ensures the models are trained on reliable inputs. Having covered the data workflow, let's explore how AI specifically enhances the core tenet of ECO-DRR, the integration of ecosystems with traditional disaster risk reduction. We have identified 4 key approaches driven by AI technology. Firstly, through ecosystem services, (S). The primary focus here is the disaster regulation service provided by ecosystems. AI helps in evaluating ES justice and performing comprehensive co-benefit evaluation. For example, assessing the combined advantages of a restored floodplain that offers both flood retention and recreation opportunities. Secondly, via ecosystem indicators. AI simplifies the ecological complexity by integrating these indicators, such as biodiversity metrics or urban forest data, into traditional risk assessment systems. This makes the complex benefits of ecosystems manageable for technical application. The third approach is dynamic change prediction. To manage the inherent uncertainty caused by ecosystem dynamics, AI uses simulation models, like cellular automata or maximum entropy models, to predict future developments and changes in the ecosystem. Finally, AI works through green infrastructure, GI, construction. GI serves as the physical spatial carrier and an important integration approach for ECO-DRR. AI leverages tools like complex network analysis to optimize GI construction and enhance its resilience against potential risks. Finally, we map where and how AI is applied throughout the 4 official procedures of ECO-DRR: assessment, implementation, and monitoring and evaluation. Starting with assessment, AI provides powerful analytical tools. This includes the determination of risk grading, zoning, and risk point identification through pattern recognition and classification algorithms. Furthermore, AI assists in the quantitative ecosystem service, ES, estimation and the critical ES justice assessment, ensuring the benefits are distributed equitably. Next is implementation, which is the most frequent application area for AI. Here, AI focuses on decision-making through optimization. Key applications include benefit cost assessment for projects like green-gray infrastructure, maximizing cost effectiveness. AI also manages complex multi-objective trade-offs, ensuring solutions maximize multiple ecological benefits simultaneously. The third area is monitoring and evaluation, M&E, which is increasingly reliant on technology. AI is essential for dynamic monitoring using sensors and data systems to acquire real-time data. It enables quick performance evaluation of implemented ECO-DRR practices and allows for real-time control of green infrastructure, GI, facilities using algorithms like RTC during a disaster event. AI is the vital engine that drives these procedures, transforming ECO-DRR from a static plan into an adaptive and dynamic strategy. To illustrate the power of AI in practice, let's look at 2 key best cases in ecological risk reduction. First, we examine flood mitigation at both the parcel and city level. This is often focused on improving stormwater response, the largest proportion of ECO-DRR cases. Here, AI-enhanced models, utilizing sophisticated algorithms like the genetic algorithm or hydrological simulation, are crucial to optimizing the design and layout of green-gray infrastructure. The core aim is to conduct multi-objective trade-offs, maximizing flood control performance while ensuring cost-effectiveness. A practical example is using machine learning to optimize the location of urban green spaces specifically for efficient runoff reduction. Second, we look at extreme heat and fire risk profiling, both significant climate-related hazards. AI's role here is centered on risk profiling and key indicator identification. Algorithms such as random forest and BP neural networks are employed to identify areas susceptible to fire and extreme heat. The underlying data insight reveals a strong correlation between land cover and land use and temperature characteristics in urban environments, guiding targeted interventions. We have reached the end of our session. Let us summarize how AI contributes to ecological risk mapping by revisiting our 3 learning objectives. Regarding our first objective, understand core AI concepts, the key takeaway is that AI provides the critical capabilities, learning, discovering, and reasoning, to effectively address the inherent uncertainty and complexity of ecosystem-based disaster risk reduction. For the second objective, explore AI technologies, we saw that machine learning and its subset, deep learning, are the powerhouses. They enable automated analysis, complex data fusion, and sophisticated pattern recognition for building accurate predictive models. Crucially, we must pair this power with explainable AI, XAI. Transparency, accountability, and adopting a value-sensitive design approach are non-trivial steps, but vital for achieving public trust and ensuring responsible AI implementation. Finally, for review integration frameworks, AI integrates ecosystems into DRR via a clear workflow. This relies on leveraging the 3 risk elements: data, hazard, vulnerability, and exposure, to train models effectively. The resultant integration approaches focus on maximizing benefits through ecosystem services, utilizing measurable ecosystem indicators, and optimizing green infrastructure.